Welcome to our chapter on light and color. Light is an electromagnetic wave that the human eye can detect. One thing that distinguishes light is that it does not require a medium. So this is something that's different than the mechanical waves we've studied so far. Light does not require any kind of material to travel through. And when we talk about a light ray, that's going to be a straight line that represents the path of a light beam, just like when we did our mirrors chapter. So you would have a straight line, it looks like a vector, but you put the arrow in the middle to indicate the direction that light would travel. You've probably seen the electromagnetic spectrum in your chemistry classes, so this is an example of some common items that you might be familiar with and their size. For us, you will need to know that the wavelength for light ranges from 700 nanometers to 400 nanometers, and also that the color ranges from red to violet. So I put some pictures on the slide for you. Remember that nano is 10 to the negative ninth, so you're going to need to know how to do that conversion. And if you're familiar with the acronym Roy G. Biv for our rainbow, that's going to show us that the color starts at red at 700 nanometers, and then it proceeds through orange, yellow, green, blue, indigo, and violet is at the 400 nanometer end of the spectrum. Now, hopefully you remember the difference between wavelength and frequency. So if you compare the wavelengths or frequencies of these different colors, you can see that as the color goes toward the violet end of the spectrum, that wavelength is getting smaller, but it has a higher frequency. We've talked about the speed of light in some other chapters, so remember this number, 3 times 10 to the 8th meters per second. You've worked with it before. Now we can apply that number to some formulas that we've already had before when we talked about waves. So instead of a plain V, the speed is going to be the speed of light, so 3 times 10 to the 8th meters per second, and that's equal to frequency times wavelength. So we can have the frequency of a certain color times the wavelength of that same color, and when we multiply those two together, the product will equal the constant for the speed of light. We can also calculate distances or times using the speed of light and simply say that speed is distance over time, just like you've seen before. So I've got a couple of examples for you. The first one asks you for the frequency of red light. Now from earlier, you should know that the wavelength for red light is 700 nanometers. And don't forget, we want to convert that to meters. So I'm going to do the shortcut version where I say 700. And instead of nano, I'm going to replace that with times 10 to the negative ninth. And then that will be in meters. We know that the speed of light is 3 times 10 to the 8th meters per second. And we're looking for the frequency. So our formula looks like this. The speed of light is frequency times wavelength. And since we're solving for frequency, you should see that we're simply going to divide both sides by the wavelength. So plug your numbers in, try this out, and come back and check your answer and see if you get the correct frequency. Hopefully you get an answer of 4.29 times 10 to the 14th. And don't forget that frequency is measured in hertz. So you should have seen that the meters canceled out and that left us with 1 over seconds, and that's the same thing as a hertz. Now for our second example, we're looking to see how far light travels in 750 kilometers. And let's just clarify that and say, how long does it take for light to travel 750 kilometers? So go ahead and take a moment and make that correction so this is a little bit clearer. So we are actually solving for a time. So our formula is going to look like this. Speed is distance over time. And remember, when we go to rearrange that, we are going to cross multiply C and T together, and that's equal to the distance. And then when we look for the time, we end up with distance over the speed of light. So let's plug our numbers in. Our distance was in kilometers, so you want to make sure that we change that. So instead of kilometers, I'm going to say 750 times 10 to the third meters, because we want our units to match up. And then our speed of light is 3 times 10 to the 8th meters per second. Our meters will cancel out with each other and we'll end up with units of seconds. So go ahead and type that in your calculator and see what you get. You should see that it's a very small time because light's really, really fast. So even though that's 750 kilometers, it only takes about 0.0025 seconds for that to happen. So when we're dealing with speed of light, you want to look for either frequency and wavelength, in which case you would use this formula. Or if we're talking about distances and time, you would use this formula. Our second section for this lesson is going to be sources of light. So we're going to be talking about things that light up other objects as well as objects that are being lit up. And then we'll apply that idea of brightness to a formula so we can mathematically solve how bright something is. So first, we're going to see these two words kind of partnered together because they're similar to each other. The first is a luminous body, and that's an object that emits light waves. And the second is an illuminated body, an object that reflects light waves. So for the luminous body, you want to pay attention to that prefix because that's going to come up later. Whenever something starts with lumen or luminous body, that's going to refer to the object that's doing the lighting, so light's coming out of it. Illuminated, so this IL in front refers to something that's being lit up, so that's the object that you can actually see. So we've got some more new vocabulary. The next term is luminous flux. Notice how it starts with luminous. That's going to be the rate at which light is emitted from a source. So it's luminous, so something's coming out of that object. Now, luminous flux is used in other formulas, so I didn't write down a specific formula for you. However, you need to know that its symbol is a capital P, and I mentioned that it's kind of like power from last semester, and the units are going to be lumens, and I abbreviated that LM. That's not a 1, that's an L. And it's similar to power. I don't know if you've ever looked at the packaging for a light bulb, but if you look at the watts, there's a lumens equivalent to that. So if we think about a power that's specific to light coming out of something, that's what luminous flux is like. You do not have to know this conversion. I just put it there as an example for you. So next time you see a light bulb packaging, look on the outside and see if you can tell how the watts equate to the lumens. The next term is luminous intensity. It's still referring to the object that's doing the lighting. Now, luminous intensity definition is the luminous flux that falls on the inside area of a sphere with a 1 meter radius. So I simplified that for you. It's basically telling us how bright the source is, so the thing making the light. And the area of a sphere was 4 pi r squared. If we are looking at a standard, this is just to set up the formula, a standard of 1 meter radius, that 1 square just turns into 4 pi. So if we look at the luminous flux for that 1 meter sphere, our formula for the intensity ends up being P over 4 pi. Now when we talk about intensity, it's a capital I, and it has this unit called a candela, or CD. Back in the olden days, it was similar to candle power, so if you think about how bright a candle would be, that's kind of where this idea comes from. Now typically we're usually not that interested in the total amount of light emitted from a source. We're more interested in the illumination that it provides on various objects. So how well lit can something be in order for us to see it better? And in order to do that, we look at a quantity called illuminance. Notice the prefix changed. It's illuminance. It's also called illumination. So this is referring to the object being lit up. Now, illuminance or illumination is the rate at which light strikes a surface. So I don't know if you've ever noticed on a flashlight that it actually does matter how far away the flashlight is from the object that you're trying to see. So that distance that they're apart is now a part of our formula. So we're going to look at E for illumination. I know that doesn't really start with an E, but that's how I remember it in my head. But illumination is P divided by 4 pi d squared. And we've had this inverse square relationship in a couple of other chapters, so it's going to be the same thing. The illumination or illuminance is inversely related to the distance squared. And when we look at our units, Lm was for luminous flux, And then 4 and pi don't have any units, but distance should be in meters, and because it's squared in the formula, it's going to be squared here. And this is called a lux. Now, I don't know why somebody can't write down all 3 letters, but it is abbreviated where you just drop the U out and it's LX. So I have a little summary for you for those of you who are pretty visual to remember these in order. It spells pi. So P was luminous flux, and I know that it's a bit of a stretch to remember this, but flux starts with an F, and if we just kind of hook those 2 parts of the F together, oh look, it turns into a P, which is the symbol. I know, it's rough. Okay. So luminous flux is measured in lumens. Next we have the I in pi for intensity. That's measured in candelas. And then remember, I told you in my head, I always say illumination for this last one, and that one's measured in lux. It's just a memory tool. You don't have to use it, but for me, visually, it kind of helps me remember which terms go with what. And lastly, we're going to do an example problem together. So we are given a 72 candela light source. This is when the units really come in handy because it doesn't tell us if that's flux or intensity or illumination. It just says 72 candelas. So if we know our units, we know that intensity is the thing that's measured in candelas. And then we know that this source is 2.65 meters above the surface of a desk. So that one obviously should be a distance. And then next we're looking for the illumination. So we're looking for the illumination. Now I'm going to show you 2 ways to work this problem. First, if we look at our formula for illumination, it's P over 4 pi d squared. And we don't have the P yet, but we can find it with our intensity formula. Remember, intensity was P over 4 pi. So I can use the intensity that we're given to help us find a luminous flux. So let's do that. So if I were to rearrange, I would say I times 4 pi, and this would give us the value for the luminous flux. And in this case, it's equal to 904.8 lumens. And now that I know this value, I can plug it in to my illumination formula and also plug in the distance and find the answer. So I'm going to take that answer that we just found, the 904.8 lumens, and then divide by 4 pi, and we know our distance is 2.65, and don't forget to square the distance when you plug that into your calculator. So try that out. And you should get a final answer of 10.25. So I'm just going to say 10.3, and then illumination is measured in lux. Now let's look at a different way we could have solved this problem. So I have my givens. Now let's look at our 2 formulas. I've got illumination is P over 4 pi d squared, and I also know that intensity is P over 4 pi. Now let's take this idea of P over 4 pi and look right here in the illumination formula. That's the same thing. I can make a substitution and say that illumination is also equal to the intensity over d squared. So this is just a little shortcut for you if you didn't want to take 2 steps. So let's plug the numbers in and see what we come up with. If we divide 72 over 2.65 squared, we get an answer of 10.3, just like we did before. So you can work this multiple ways, and remember that you want to pay attention to your units so that you can identify your variables correctly. That's it for this lesson. Next time we're going to look at light and matter.